as we were getting into trying to come up with materials that would be able to stand the ballistic reentry for ballistic missiles, I began to look at various kinds of materials that would be able to do the job. And we studied different metals. Copper at that time, a very, very highly polished copper surface was one of the concepts that had come up with, the Air Force had come up with for being able to, and the fact that it would be highly polished would minimize the kind of frictional scrubbing action on the surface and lower the heating. So that was a concept that was being worked on, and then we looked at other kinds of materials, what they call ablative materials. And the ablative material, actually there is a chemical reaction between the material and the boundary layer that occurs in the boundary layer, because these materials were organic kind of materials, and but the boundary layer, even though it was at fairly high temperatures, it still protected the basic material underneath from the very, very high temperatures that could be achieved by the airstream outside of the boundary layer. That was the basic concept. And I studied a number of materials. Teflon was one of the good ablators, but it had some other properties that were not quite as good as the kind of material that ended up testing for working on the Mercury. I'm kind of getting ahead of myself a little bit. Back, I guess it was sometime in 1957, and I have brought along a copy of a report that I did on experimental ablation cooling. And this report gave the results of a number of materials that were studied in ground test facilities to study the physical properties of how ablators worked in very hot airstreams. And back in those days, the only way that you could get a very hot airstream was to either using an electric arc to heat the air, or one of the new innovations there at Langley was a pebble bed heater. We it was a long column, cylindrical column that was filled with zinc oxide pebbles. These pebbles were then heated to a very, very high temperature of 2,000 to 3,000 degrees. And once they were heated, then the air was flowed through the, at fairly high velocities, flowed through these ceramic pebble bed and picked up the heat, and then exited as a regular wind tunnel. And we used, again, specimens of different materials to study the effect of heating on them. That was one of the facilities that I used. Another one was the University of Chicago had arranged to use an old streetcar barn where they had big electric generators to produce an arc jet that would produce a bigger jet than what we had at Langley, and at fairly high temperatures, again in the 2,000 to 3,000 degree range. And I took several models up there and tested them.